So let's start. You know that in last consultation, we have focused on these topics, that is contour integration, or how we can solve contour integrals if the path is given as a circle. We have also learned how to solve Cauchy's residue theorem. And by using Cauchy's residue theorem, we have learned how to solve improper integrals. So today, our focus will be on Taylor and Laurent series. But before that, we will solve some complicated problems from this part. Okay, then we'll move to the next section, that is Taylor and Laurent series. So just to recall the previous study, let me write one problem here from Cauchy's residue theorem. So let's say we have to evaluate the integral sine pi z over z negative 2 squared dz, where C is the circle, or you can say C is the contour that is defined by modulus of z equal to 3. So this is our complete question, and we have to evaluate this integral by using Cauchy's residue theorem, or in short, we know it is CRT. So this problem can be solved by Cauchy's residue theorem. First of all, we have to find the poles, and then we have to determine what is the order of that pole. Okay, if the order is 1, then we can understand that we can apply the basic formula. And if the order is greater than 1, then we have a general formula for finding residue. And the order can be defined by the power of the factor. You can see here we have z negative 2, that is the factor with power 2. So order of the pole 2 will be 2. So you can remember that in Cauchy's residue theorem, we have to find residue at first. After finding pole, we have to find residue of that pole that is inside and on the contour. So residue at z equal to any point A can be found by this way, that is limit z tends to A or z approaching to A 1 over m minus 1 factorial d power m minus 1 dz power m minus 1 z negative A power m f of z. If this pole is of order m, then we can find a residue by this way. But if this is of order 1, that is, we have to find a residue, let's say residue of z equal to A, that is of order 1. That means the value of m is 1. That means 1 minus 1 factorial, that is 0 factorial, 0 factorial is 1. And if we simplify d power 1 minus 1, d power 0, that is 1, dz power 1 minus 1, 0. So finally, we are having only limit z tends to A or z is approaching to A. This part will be 1, and just we will left with z negative A f of z. So this is the special case. If the pole is of order 1, then we can apply directly this formula. And if the pole with order m, then we can apply the general case. So in last consultation, we have solved some problems with this formula. Now we will focus on this. So first of all, I hope you can remember all the steps that can be applied to solve any integral by using Cauchy's residue theorem. So first step, Step 1. Step 1 says that we have to find the pole or singularity or singular point of the function. Here the function is f of z, because if we compare with integration of f of z dz, then this part is this one. So here the function f of z is equal to sine pi z over z negative 2 squared. This is our main function. Now step 1. Step 1 is to find pole, or we can say we are going to find pole. So finding poles is our main target in step 1. So I hope you can remember that pole can be found by the formula denominator equal to 0. If we consider this one, then in denominator portion the upper part is numerator and the lower part is denominator. So in denominator portion we have z negative 2 squared equal to 0. That means we are getting z negative 2 equal to 0, and finally z equal to 2. So z equal to 2 is a pole, or we can say this is the singularity or singular point. So you can remember the definition of pole or singular point. That is, pole or singular point or singularity can be defined by that a point where the function is not analytic. You have the function f of z, you can input z equal to 2 here, automatically the function is giving you something by 0 that is undefined. So if it is undefined, it is sure that the function will not be analytic at that point. So z equal to 2 is called a pole because the function is not analytic here. Okay, do you understand my point? So we are just recalling our previous. Okay, thank you. So now we can leave a comment that here f of z has a pole at z equal to 2 of order what? You can have a look on the power of the factor z negative 2. Z equal to 2 is coming from this equation, z negative 2 squared equal to 0. That means z negative 2 with power 2. So that power is the order. That means here m equal to 2. So here f of z has a pole at z equal to 2 of order 2, or we can say of order m equal to 2. So you know that if a pole is of order 2, that is called a double pole. If a pole is of order 1, that is called simple pole. So here we have a double pole. So we have given a comment here so that we can understand. Now let's move to step 2. In step 2, we have to find the residue. So finding residue at z equal to 2. But before that, we have to draw the region that is given. So here we have modulus of z equal to 3. We have to check whether this pole is lying inside this circle or not. If it is lying outside the circle, then residue will be ignored. Okay, but if it is inside or on the circle, then we have to find a residue. So we have the region, that is the contour C, is defined by modulus of z equal to 3. So I hope you already understand that modulus of z equal to 3, that is obviously a circle, but let me write clearly here. So this is going with chapter 1 concept. So where we have z, we are just replacing z by x plus yi. So now we have real part and imaginary part. Just to remove absolute value, we can use this way. Square root of x squared plus y squared equal to 3. If we square on both sides, then we will get x squared plus y squared equal to 3 squared. That means this is the equation of circle with center 0, 0. and radius 3. So from here we can understand that this is the equation of circle. Here center is 0 0 and radius is 3. So let's draw this circle. The meaning of modulus of z equal to 3 and the meaning of this one is same. So our radius is 3 and center is 0. So let's locate the center at first. From here we have to move 3 distance, 1 2 3, 1 2 3. Now we can draw our circle with free hand. So this is the circle modulus of z equal to 3. Now we have to understand, or we have to check whether the pole is inside or on. So we have z equal to 2. Now you know that z equal to 2 is actually a point z equal to 2 plus 0i. That means z equal to 2 can be written as also 2 plus 0i or a point 20. So that means this is our pole z equal to 2 or z equal to 2 plus 0i, or we can say the point is 20. Any complex number is a point. So let's locate the point 20. Is 20 inside the circle?
Yes, sir.
Yeah. That means 1 2 3. So 2 is here, 20. So that means z equal to 2 is here. In this point, the function is not analytic. That's why this is called the pole. But since it is inside this region or this circle or this contour, we have to find the residue now. So we can also leave a comment here, that is here f of z has, same comment can be given, f of z has a pole at z equal to 2, which is inside the circle. So we can leave a comment that z equal to 2 is inside or within C. We can use any word, within or inside. So now let's find the residue. So residue at z equal to 2. Remember, z equal to 2 is a pole of order 2. So here,
স্যার এখানে যদি z equal to 2 না হয়ে z equal
yeah, z equal to, sorry, I
3
didn't get
হলে
you. 3.
z
Okay.
equal to 3 হলে হ্যাঁ
If z equal to 3, then we have to also find the residue because it is on the boundary, inside and on. Okay, it may be inside or on, but if it is outside, if the pole is outside, then we don't need to find the residue. Do you get my point?
yes sir.
Suppose instead of z equal to 2, we have z equal to 3, okay, or z negative 3 squared, but 3 is on the boundary, that is on the circumference of the circle, so we must have to find the residue. That's why Cauchy's residue theorem says that you have to find the residue if the pole is inside or on. Inside and on, or inside or on. Is that okay? So let's use this formula now because m is 2. So r equal to residue at z equal to 2. You can compare with z equal to a, so the value of a is 2. Or we can also write this one as residue of f of z, comma 2. That means we are going to find the residue of the function at pole 2. We can use any notation. So the formula is, you can remember the formula is limit z tends to a 1 over m minus 1 factorial d power m minus 1 dz power m minus 1 z negative a power m f of z. So this is our main formula. Now we can input the value of m so that we can simplify. So here limit z tends to a, that means z tends to 2, 1 over the value of m is 2, so 2 negative 1 factorial d power 2 negative 1 dz power 2 negative 1 z negative a is 2, so z negative 2, m is 2, f of z, f of z is our main function, this one, that is sine pi z over z negative 2 squared. So we have replaced whatever parts we need. So that means sine pi z over z negative 2 squared. This is the function. So here you can easily understand that limit z is approaching to 2. This part will be 1 negative 1 factorial. That means, sorry, 1, and in denominator we have 1 factorial. So that means this is giving us 1. And here 2 negative 1, that means d power 1 dz power 1. So we have here z negative 2 squared, z negative 2 squared. So before differentiation you can see that we can simplify. We can simplify that this part and this part are same. So we have the simplified part, that is just sine pi z. Is that okay?
Yes, sir.
So now from this part we can write limit z tends to 2, this is 1, and this becomes d dz. So this is the first derivative of sine pi z. We have to differentiate now this function in terms of z, and pi is constant. So we can apply chain rule, you know that, or we can directly solve. If we have d dx sine ax, what is the formula? It will be a cosine ax, right?
Yes, sir.
Or we can apply chain rule, that is d dx of sine ax. That means we don't know, suppose this formula, we just know d dx of sine x, then we can write cosine x. So same part can be done here. Consider this part as x, so differentiation of sine x is cosine x. The part that you have considered, that should be again under differentiation. So finally cosine ax, and differentiation of ax is a. So this part and this part same, so we can establish this formula. So it will be limit z tends to 2, limit z tends to 2, the result is pi cosine pi z. Now this is becoming a limiting problem. We have to input the value of z where we have z. So let's input, it is pi cosine pi z. That means we have pi 2 or 2 pi. We are plugging z as 2. So cosine 2 pi, that is 1. So we have just pi. This is our residue r. Or we can say residue r1. Since we have one pole, we can also denote by r1. So finally, we are able to find the residue of the pole for that function. So now it's step 3. What is step 3? Can anyone please mention? Step 3 is to find the result of the integral. So result of the integral can be found by using Cauchy's residue theorem. And the theorem says that the integral that you have, that will be equal to 2 pi I sum of all residues. Since we have only one residue, R1. So 2 pi I, R1 is pi. So that is 2 pi squared I. This is our result. This is the result for the integral that we have. Integration of sine pi z, z negative 2 squared dz. So we have found the result. Is that okay?
Yes, sir.
So in last consultation, we have worked just with simple pole, and now we have worked with the general case, that is m is now 2. So I hope you have understood this problem also. So Cauchy's residue theorem can be applied in improper integral, So let's focus on improper integral now. You will again get the application of Cauchy's residue theorem. So let's take one problem from improper integral. Okay, but before that, I would like to highlight one point, that is, you can see if we have to evaluate one integral by using Cauchy's residue theorem, then we have to find the pole at first. So for this, denominator equal to 0, and we are solving one equation that involves complex number z. So till now, from last consultation to this problem, whatever pole we have found, that is in rectangular form, not in polar form, right? We can express this one as x plus yi or 2 plus 0i. Is that okay? Do you get my point?
Sir, can you repeat?
That means for evaluating any integral by using Cauchy's residue theorem, at first we have to find a pole by using this concept, denominator equal to 0. Is that okay?
Yes, sir.
And think about this problem. We have solved this equation and finally we are getting z equal to 2. So z equal to 2 can also be written as z equal to 2 plus 0i. So this is the rectangular form of complex number. Is that okay?
Yes, sir.
But we have also another form of complex number that is called polar form, right?
Yes, sir.
So sometimes it is possible to have polar form as the result, as the pole. So what we have to do at that time? Is that okay? I am asking about that part. Have you understood the question?
স্যার এটার মতোই করতে হবে না, যেমন পোলার ফর্মে যদি এরকম 2 + 0i থাকে তাহলে
The process is same. At first, step 1 is to find pole, step 2 is to find the residue, and step 3 is to evaluate the integral by using 2 pi I sum of all residues. But if we have polar form, then there will be some changes. Okay, let me take one problem from improper integral and you will understand from here. I have already mentioned that in this consultation I will discuss with complicated problems, so that's why I am mentioning that one. So now we are going to solve improper integral. I hope you have watched the BX videos, or you have watched my last consultation videos. I think you have the minimum idea of improper integral. So improper integral can be of negative infinity to infinity f of x dx. Here f of x is a real valued function, or it may be 0 to infinity f of x dx, or a to infinity f of x dx. It may be minus infinity to b f of x dx. So we have so many things. Despite having infinity at upper limit, infinity at lower limit, infinity at both the limits, the result may be finite, may be infinite. So if it is finite, it is called, if we get a finite value, finite complex number, then it will be convergent. So this concept is going with your Math 120 course, okay? And if we get infinity again, that will be divergent. So we don't need all these things here. This is the short overview of improper integral. But we have to solve improper integral by Cauchy's residue theorem. So let me take one problem. Suppose we have to evaluate the integral negative infinity to positive infinity 1 over x squared plus 1 we will start improper integral later after this problem. Let's try to understand by another problem. Again, I am confined in Cauchy's residue theorem. Okay, let's say evaluate the integral z to the power 1 over z to the power 4 plus 16 dz. So here the contour can be defined as, so evaluate the integral where C is the upper circle from z equal to -4 to z equal to 4. Okay, this is the complete question. We will focus on improper integral later, but for now try to understand this one. So we have to evaluate this integral where C is the upper circle from z equal to -4 to z equal to 4 by using Cauchy's residue theorem. And you know that Cauchy's residue theorem says that the integral f of z dz, that will be finally 2 pi I sum of all residues. If we have 4 residues, then it will be 2 pi I r1 plus r2 plus r3 plus r4, like that. So this is Cauchy's residue theorem. Now, what will be step 1?
Finding poles.
Finding poles. So let's find pole. So for finding pole, we have the formula, that is denominator equal to 0. So in denominator portion, you can see that we have z power 4 plus 16. So, but before that, I would like to write the function f of z. So f of z is this one, 1 over z to the power 4 plus 16. So here, the denominator is z to the power 4 plus 16 equal to 0. Now, try to think about this equation and the previous one that we have solved earlier, z -2 whole squared. So this problem can easily be solved, that is, we are getting z equal to 2. Or you can think about the last problems that we have, the problems that we have understood in last consultation. Okay, the only difference is here. Our target is to find the poles A, B, C. How many poles we will have here since z power 4 is here? There will be,
4.
this is one equation, right? So there will be 4 poles. Now think about how we can find all the poles. Can you figure out? It is the concept of chapter 1. In chapter 1 or from week 1, week 2 contents, you know that how to find roots. Right?
Yes, sir.
So this is our equation, z to the power 4 plus 16 equal to 0. So what we have to do, we can apply de Moivre's technique to find all the roots. Is that clear?
Yes, sir.
And you might know that theta is equal to theta plus 2k pi, where k is 0, 1, 2, 3, 4, or negative 1, 2, negative 2, negative 3, negative infinity, like that. So this is the formula. First of all, we have to solve this equation. So we are getting stuck at this part, but the process is same. We are in step 1, then we have to find step 2, then we have to move to step 3, but we are getting stuck at this part. So this concept is going with chapter 1. So what we can do, we can solve this one. So z to the power 4 equal to negative 16. We are keeping negative 16 on the right side. So try to recall your week 1, week 2 contents. You will get the idea from here. So now it can be written as 1 over negative 16 power 1 over 4. Is that okay up to now?
Yes, sir.
Okay, we are targeting for all the poles. We are sure that there will be 4 poles. Now these are called roots. So roots are becoming poles. Okay. So can anyone remember what we have to do now? Week 1 contents are the very basic part, because without that contents, without that concepts, we can go forward. Okay, so these things is coming here. This is a rectangular number, right? And this part should be converted to polar form. Is that okay? So the part that is inside the parenthesis, it is a complex number, negative 16. Or we can think about negative 16 plus 0i. Now, this complex number is a point, negative 16, 0. So, negative 16, 0 is in this quadrant, second quadrant, right?
Yes, sir.
So, you can easily understand that the angle theta will be pi. Okay, but we can apply our basic skill. That is, at first, let's find modulus r, because our target is to convert this number to polar form r e to the power I theta. Then only it is possible to apply this formula, that is theta equal to theta plus 2k pi. Okay, so r equal to x squared plus y squared square root. That means here x squared will be negative 16 squared and y part is 0, so 0 squared. So that means we are getting 16 squared, negative squared is positive. So actually we have 16. Is that okay?
Yes, sir.
And theta equal to, we know that tan inverse or arctan y over x. So tan inverse y is 0 and x is negative 16. So we are getting tan inverse 0. That means we are getting 0. Is that okay? Clear? So the angle that we have found That should be corrected. Okay, so we can see from the second quadrant that the point is in second quadrant. So what we have to do with this angle, what we have to do, we have to add 180. So actual angle is, depending on the location of the point, we have found theta as 180 degree, or it is 180 degree is pi. Is that okay?
Yes, sir.
First tell me, can you remember your previous contents? We are just using these concepts. Okay, so we have found r and theta, that is z. So z equal to r, value of r is 16, then e to the power I, theta is pi. Power 1/4. So now we have to input theta equal to theta plus 2k pi. So z equal to 16 e to the power I, this is theta. So that should be theta plus 2k pi. So pi plus 2k pi. Is that okay?
Yes, sir.
And we have power 1/4. So it is called de Moivre's formula. Now, since we have mentioned k here, so we can also use z as zk. So this is becoming this one. So now you know that if we have mn power, or we can say if we have ab power m, then we can write a power m, b power m. This is the property. So think about this one. We have one part, another part. So it can be written as 16 power 1/4 e to the power I pi plus 2k pi times 1/4. Or we can write here also. Is that okay?
Yes, sir.
So 16 power 1/4. Can anyone please tell me what is the simplified part? It is 2, right?
Yes, sir.
E to the power I pi plus 2k pi over 4. This is zk. So finally, we have found a relation from where we can find all the roots. So from this equation, we can understand that there will be 4 roots. So we can start from k equal to 0. If we start from k equal to 0, then we have to stop at 3. 0, 1, 2, 3. So 1, 2, 3, 4. We will found 3 roots. Here. So let's start with k equal to 0. Or for better understanding, I am using a table so that you can understand properly. So k, and we have the root zk equal to 2 e to the power I pi plus 2k pi. I am using another color here, zk and 2k pi. Okay, we have to input k. So k equal to 0, 1, 2, 3. 0, 1, 2, 3. Then we will get z0, z1, z2, z3. Is that okay? Okay. First of all, you can understand that this is a polar form, r e to the power I theta. Is that okay?
Yes, sir.
So what is the radius of this part or modulus? It is 2.
2.
So it will be obviously a circle with radius 2. Okay, so let's find this one. So if k is 0, so what will be the result? Let's find. It will be 2 e to the power I pi plus 2k pi. So k is 0, so that means we are getting e to the power
Pi by 4.
pi by 4. Thank you. So this is the first part. And then if k is 1, we'll get 2 e to the power I pi plus 2 times 1 times pi. So 2 pi. So 2 e to the power I 3 pi by 4. Clear? This is the second root. Third root, 2 e to the power I pi plus 2 times 2. We are plugging k here. So 2 times 2, 4. 4 pi by 4. So that means 2 e to the power I 5 pi by 4. For the last one, 2 e to the power I pi plus, now input 3, 3 times 2, 6. So 6 pi by 4. So 2 e to the power I 7 pi by 4. Clear?
Yes, sir.
So here you can see that pi by 4 is actually 45 degree. 3 pi by 4, that means it is 135 degree, right? And 5 pi by 4, 5 times 45, 225 degree. 7 times 45, 315 degree. Just I am using degree notation so that you can easily understand what is the angle for every roots. Is that okay? So
Yes, sir.
whatever concept we have applied, that is going with our week 1, week 2 videos. But don't forget that we are in Cauchy's residue theorem. So we have to go a long way. That is, our target is to solve this integral. But for solving this integral, at first we have to find a pole, and this pole is becoming an equation. From this pole, that means from denominator, we have this part. So that is one equation. So from that equation, we have found all the values of z. So that means now we are able to solve this. So we have found 1, 2, 3, 4 values. Is that okay?
Yes, sir.
So let me write again. So from this part, I am writing. This is the continuation of that part. So still we are in step 1. Step 1 is continuing. So we had z to the power 4 plus 16 equal to 0, and finally after using this concept we have found the values for z. So we have found total 4 roots: z0, z1, z2, z3. Is that okay?
Yes, sir.
So I am not writing z0 again, just I am denoting with this point: z0, z1, z2, z3. So step 1 is done. So this is the difference between the previous problem and this problem. In previous problem, we have found z equal to 2. That is the rectangular form, x plus y I, 2 plus 0 I. But here, what we have found? We have found 2 e to the power I pi by 4, 2 e to the power I 3 pi by 4. So that means r e to the power I theta is coming. That means we have found the polar form. And we know how we can convert polar to rectangular. You can also do by that way. But I am trying to make you understand, if we have polar form, how we can deal with this to evaluate the integral by using Cauchy's residue theorem. So I am not converting this one to rectangular form. If you want to convert this one to rectangular form, you can do. But let's try to figure out how we can work with polar form also. Have you got my point?
স্যার এর আগেরটাতে তো আমরা চাইলে মানে পোলার ফর্মও নিতে পারতাম, মানে z
Yeah,
ইকুয়াল
yeah,
টু যেটাতে
yeah.
ছিল।
So that means the main concept is we can work with both rectangular form and polar form. Okay. So we have worked with rectangular form several times in last consultation and today, but now we are using polar form. So step 2. Step 2 is to find a residue, right?
Yes, sir.
Finding residue of that poles. We have total 4 poles which are inside or on the boundary of the contour, or which are inside the contour or on the boundary of the contour. So now focus on the contour. What contour we have? We have the upper circle. That is from z equal to -4 to z equal to +4. If you draw this one, this is z equal to -4, z equal to +4. So we have the upper circle. This is the thing. Okay. Is that okay?
Yes, sir.
So we are going to draw our region. This is an upper circle from z equal to -4 to z equal to 4. You don't need to think about this. It will be given in your question. That means this is the contour. So let's draw this one. Z equal to -4. This is a complex number. -4 plus 0 I or -4 0 point. So -1, -2, -3, -4. This point is z equal to -4. And z equal to +4, that will be 4, 0 point. So on right side, 1, 2, 3, 4. So this is z equal to 4. And since this is the upper circle, so in upper part we have also the same distance 4. So now we can draw the contour. So this is our given contour. See, we have to check out of these 4 poles, which poles are inside or on and which are outside. Have you got my point?
Yes, sir.
Okay. So you can see that Z0 is 45 degree, Z1 has an angle 135 degree,
So আমাদের
Z2
এটা
has
তো নিউমেরিক ভ্যালু বের করে চেক করতে হবে।
yeah, or we can do by another way. That's why I have written the angles here. So can you see what is the radius of every poles? What is the radius of every poles?
Yes, sir.
What is
2.
the radius? 2. So that means we can leave a comment here that f of z means that function 1 over z power 4 plus 16. Or now we can write by another way. It is actually z negative z0 times z negative z1, z negative z2, z negative z3. If we multiply all the factors, we will get z power 4 plus 16. Is it clear?
Yes, sir.
So we have found the poles, but order of every poles is 1. Is that okay? How I have written this one? Because the previous line of this part will be z negative z0 times z negative z1 times z negative z2, z negative z3 equal to 0. And you have z0, z1, z3, z2, z3 from this part. So if it is possible to multiply all the things, you will get this part back. So that's why z to the power 4 plus 16 can be written in this way. We have done a similar problem in last consultation. You can remember. So here f of z has 4 poles at z equal to z0, z1, z2, z3. Each of the poles with order 1. Is that clear?
Yes, sir.
Now, you can see that we have all the poles. Now we have to check which pole is inside the circle. So since we have the radius 2, so it is radius 4. So for every roots, you know that every roots of an equation will lie in the circumference of a circle. If it is a circle and z to the power 4 plus 16 has 4 roots, so all the 4 roots will be in the circumference of a circle with same radius. So that means we can think about a circle with radius 2. So here we have radius 1, 2, 1, 2, 1, 2. That means we can consider a circle here. Okay. So Z0, you know that Z0 is with angle or argument 45 degree, right?
Yes, sir.
So try to understand. 45 degree is in first quadrant. This is 45 degree.
Yes, sir.
So Z0 is here. Now, what is for Z1? Z1 is 135 degree. We have already understood this part. Okay. So this is 135 degree will be in second quadrant. Any complex number can be directed as a vector. So that's why we have directed this one. So this is 135 degree from x-axis, positive x-axis. Are you getting the idea?
Yes, sir.
Now let's look at Z2. So Z2 is giving us the angle 2 to 5 degree. That means 225 degree. So 225 degree will be obviously here. Is that okay?
Yes, sir.
And now for Z3, the last pole, we have 315 degree, 315. It is 360 degree, it is 270, so 315 will be here. So that is Z3. Now, have you understood the concept?
Yes, sir.
So just remove this white circle. So now think about, out of the 4 poles, which pole are inside the given contour?
So 0 and 1, Z0 and 1.
Z0 and 1. That is the idea. So only Z0 and Z1 are inside, and Z2, Z3 is outside. So this will be ignored. That means we don't need to find the residue for Z2 and Z3, but we have to find the residue for Z0 and Z1. Is that okay?
Yes, sir.
Okay. So now we are sure that we have to find the residues of the pole Z equal to Z0 and Z1. And these are of order 1. So since it is of order 1, we can apply the formula. You know that residue at Z equal to A, if it is of order 1, then we can apply the direct technique. Z tends to A, Z negative A, F of Z. Clear?
Yes, sir.
Okay. So let's find the residue of Z0. Now we are in step 2. So step 2 is continued. That is residue at Z equal to Z0. So also Z0 is 2 e to the power I pi by 4. So this is Z equal to A. That means Z equal to A. So residue. We have total 2 poles inside. So for pole 1, we can say R1. For pole 2, we can say R2. So we are mentioning first residue as R1. That is residue at Z equal to 2 e to the power I pi by 4. Clear?
Yes, sir.
So now limit Z tends to A. A is this one. 2 e to the power I pi by 4. Z negative a. So z negative this one, 2 e to the power I pi by 4. And the function f of z. So the problem is looking difficult, but actually the process is same. So z negative 2 e to the power I pi over 4. The function f of z is this one or this one. So if we take this part, then z negative z0, that means z negative 2 e to the power I pi by 4, and this part can be cancelled. Is that okay?
Yes, sir.
But we have to multiply the rest things, that is z negative z1 times z negative z2 times z negative z3. So calculation is becoming huge. So that's why what we can do, we can just work with this part also. See how we can work. So f of z is 1 over z to the power 4 plus 16. I have mentioned that today we will discuss some complicated problems, and these are the complicated problems. But the process is just same as before. So limit z tends to 2 e to the power I pi over 4. We can just write this one in upper part, 2 e to the power I pi over 4. That means we are writing this one here. This part times 1, this is here. So over z to the power 4 plus 16. Now, this is a limiting problem. We have to solve this limiting problem. So limiting problem can be solved by algebraic manipulation, can be solved by squeeze theorem, can be solved by other techniques. Or if we have 0 by 0 form or infinity by infinity form, we can apply the L'Hopital rule also. So let's check. If we input z here, so 2 e to the power I pi by 4 can be replaced here. So same thing is here. So a minus a is 0. So 2 e to the power I pi by 4, negative 2 e to the power I pi by 4, that is 0 in upper part, right?
Yes, sir.
And if we input the same thing here, something power 4, that means 2 e to the power pi by 4, power 4 plus 16. What will be the result here?
So 16.
No, it will be 0 because,
Yes, sir. 16 plus 16.
yeah, that means negative 16. It will be negative 16.
Yes,
Okay,
sir.
because we have found all the values from this equation. That means all values can be satisfied. All values will satisfy this equation, so that left side and right side will be 0. Okay, so that means obviously we don't need to calculate. By our intuitive concept, we can easily understand that it will be, the lower part will be also 0. If you have time, you can also check or verify. So that means this is of 0 by 0, so we can apply L'Hopital rule now. Is that okay?
Yes, sir.
So limit z tends to 2 e to the power I pi by 4. So do you know what L'Hopital says?
Yes.
Mathematician L'Hopital says that we have to differentiate. If we have 0 by 0, then we have to differentiate upper part and lower part at the same time. Okay. So here it will be, if we differentiate z in terms of z, so it will be 1. If we differentiate z to the power 4, we will get 4z cube, and differentiation of constant is 0. Okay. Now, this is R1. If this exists, then the result will be found. So, okay, now we can input this part, because in upper part we have 1, it is not 0. So L'Hopital rule can't be applied anymore. So we can directly find the result. 1 or z cube. So z is 2 e to the power I pi by 4. So, okay, just give me 1 minute. Okay, I have moved to another page because the previous one is finished. From this part, R1 equal to we can write it is 1 over 4. Now 2 cube, that is 8,
Yes, sir.
e to the power I,
3 pi.
3 pi by 4. Okay. So that means we can write it is 1 over 32 e to the power I, 3 pi by 4. Or we can write this way, 1 over 32 e to the power I negative, or e to the power negative I 3 pi by 4. This is R1. Okay, so let's move to R2. R2, that is residue at Z equal to Z1, because we have another pole that is inside. So Z1 is 2 e to the power I 3 pi by 4. I don't know whether you are understanding or not.
Sir, we are understanding.
Okay. 2 to the power I 3 pi by 4. Okay. So again, since this pole is of order 1, so again we can apply the same formula. Limit z tends to a, z negative a, f of z. So now let me write this one. A is 2 e to the power I pi by 4, 2 e to the power I, sorry, 3 pi by 4. Okay. Now the function that we have, function is same. It is 1 over z power 4 plus 16. Okay. So limit z tends to 2 e to the power I 3 pi by 4, z negative 2 e to the power I 3 pi by 4, and 1 over z to the power 4 plus 16. So now this part can be written here because 1 times something, that is something. So equal to limit R2 equal to limit z tends to 2 to the power I 3 pi by 4, z negative 2 e to the power I 3 pi by 4 over z power 4 plus 16. Again, now it is becoming a limiting problem. So we can input this part here. So same part with positive and negative. So it will be 0. Is that okay?
Yes, sir.
And since this is the pole, this is the 0 of the main equation or root of main equation, we can understand that if we input here, that part with power 4 will become negative 16. So negative 16 plus positive 16, it will be obviously 0. So that means it is 0 by 0. Now again, we can apply L'Hopital rule. So limit z tends to 2 e to the power I 3 pi by 4. If we differentiate this one, it will be 1. If we differentiate this one, it will be 4z cubed. Now we can input. So limit z tends to 2 e to the power I 3 pi by 4, 1 over 4. Z is this time 2 e to the power I 3 pi over 4 cube. So that is 1 over 4, 8 e to the power I 3 pi by 4 times 3. Actually, you are getting 9 pi by 4. Okay, this is R2. So finally, R2 is 1 over 32 e to the power I 9 pi by 4. Or we can write in this way, 1 over 32 e to the power negative I 9 pi by 4. This is finally R2. Okay, step 1 and step 2 is done. Let's move to step 3. So in step 3, we have to find the result of the integral by using Cauchy's residue theorem. So this is our integral. So integral f of z dz, that will be 2 pi I sum of all residues. So you know we have total 2 residues, r1 plus r2. So 2 pi I r1. What is r1? Is 1 by 32 e to the power negative I 3 pi by 4. Right?
Yes, sir.
So 1 by 32 e to the power I negative I 3 pi by 4. R2. R2 is this one. 1 over 32 e to the power negative I 9 pi by 4.
4.
Okay, so this is our result finally. You will get full marks up to this part. But we can also simplify this one. Let me simplify. Then you will understand what will be the final
স্যার
result.
লাস্ট পার্টটা একটু দেখতে পারি?
Yeah?
লাস্ট পার্টটা মানে স্টেপ 3 টা একটু দেখতে চাচ্ছিলাম।
Yeah, step 3. We have just replaced R1 and R2.
ওকে স্যার।
Okay. So from this part, we can write the integral f of z dz, that is equal to 2 pi I. 1 by 32 can be pulled out because this is in both parts. Now we have e to the power negative I 3 pi by 4 plus e to the power negative I 9 pi by 4. You don't need to simplify this one, but I am showing you how we can simplify. You know that we have Euler formula, e to the power I theta, that is cosine theta, plus I sine theta. If we have e to the power negative I theta, that will be cosine theta negative I sine theta. So we can apply this one. 2 pi I 1 over 32 e to the power negative I 3 pi by 4. So it will be cosine 3 pi by 4 negative I sine 3 pi by 4 plus 9 pi by 4 e to the power negative I theta I 9 pi by 4. So again cosine 9 pi by 4 negative I sine 9 pi by 4. Now use calculator, you will get the result. So cosine 3 pi by 4, it is most probably negative 1 over root 2. Sine 3 pi by 4, it is also I sine 3 by 4 negative 1 over root 2. Please do with me because maybe I am wrong. So cosine 9 pi by 4, that will be plus 1 over root 2, and here negative I sine 9 pi by 4, it will be negative I 1 over root 2. Okay, just verify whether my part is correct or not. So finally 2 and 32, the reduced part is 16. So we have pi I times 1 over 16. You can see 1 over root 2 plus 1 over root 2. Here negative positive, so this part are cancelled, and we have negative this one, negative this one. So that means it is becoming negative 2I 1 over root 2. Clear? So finally simplified part can be negative pi I, that is pi I squared 2, and here 16 root 2. Or we can simplify again, that is negative pi I squared is negative 1. Is that okay?
Yes, sir.
So we can write just
2 pi.
2 can be simplified with 16.
Yes, sir.
So we have just pi root 2 over 16. That means, yeah, that is done. Or we can also write this one as pi over 8 root 2. And that is also okay. So this is our result. Okay, this is the result for integral 1 over z to the power 4 plus 16 dz. Okay, finally this is done. But the concept that we are applying, that is Cauchy's residue theorem, and we are getting stuck because we have found the poles from this type of equation where the root will, the number of root will be 4. Okay, that's why this problem is getting critical. So let's move to improper integral now. I will take another same problem so that you can understand again. Or we can move to Laurent series. But I think we should practice again from another problem. Is that okay? Do you agree?
Yes, sir.
The problems are looking different, but actually the process is same. Okay. Let's say we have an improper integral negative infinity to positive infinity 1 over x to the power 4 plus 1 dx. Okay, this one. So you know that this is one improper integral, and if we have to solve improper integral, we can apply the concept that we have learned in our previous days, that is in math 120. But since it is math 215, so that process is not applicable here. You have to go through complex integral. So this problem can be solved by Cauchy's residue theorem. Okay, I'm taking the same problem so that we don't need to solve again and again. So we have this improper integral. This is the function f of x. F of x equal to 1 over x to the power 4 plus 16. Is that okay?
Yes, sir.
Yes, sir.
And okay, first tell me, should we go for 1 or 16? If we take 1, then it will be a different problem. And if we take 16, then we can save our time and we can give our time on the next content, that is Laurent series.
Sir, different problem এ গেলে I guess ভালো হয়. Same time to
Okay, let's work with x to the power 4. X to the power 4 plus 1. So this is f of x equal to 1 over x to the power 4 plus 1. And the corresponding f of z. Can you remember that if we have improper integral, we have to find the corresponding complex valued function? In last consultation, we have discussed.
Yes,
So
sir.
the main formula is we have to apply Cauchy's residue theorem. But before that, this problem can be solved by this way. That is, this is the improper integral, but we have to work for complex integral. So complex integral f of z dz, that is equal to negative r to positive r. Since negative infinity and positive infinity is a big thing, so that's why we are considering a bounded upper circle with radius r, but we will mention that r is tending to infinity. So that is now okay. So here f of x dx plus a contour cr f of z dz. I am not repeating this one because we have discussed this one in previous consultation. So here we have limit r tends to infinity, and you know that this part will give us 0, right?
Yes, sir.
And this is same as negative infinity to positive infinity, f of x dx. We can say this is I, or this integral can be denoted as I. So this is equal to integration of f of z dz. That means f of z is this one, 1 over z to the power 4 plus 1 dz. So this is the main integral. So if we have to evaluate this integral I, so we have to focus on the complex integral. Is that okay? So whatever value we will get for this one, that will be the same as for this one. And remember, in complex integration, we have some contour, but since it is improper integral, the contour will be the upper circle, negative r to positive r. So now our focus is to find I equal to infinite integration of 1 over z to the power 4 plus 1 dz. So this is now contour integral, and the contour is upper circle from negative r to positive r. Okay, now step 1 is to find poles. So for poles, we know denominator equal to 0. That is z to the power 4 plus 1 equal to 0. So z to the power 4 plus 1 equal to 0 will give you 4 roots, right?
Yes, sir.
So that means what we can do, z to the power 4 negative 1, z equal to negative 1 power 1 over 4. So finally we have found z equal to negative 1 power 1 over 4. So that means this is a complex number, negative 1 plus 0i. Negative 1 is equal to negative 1 plus 0i, or this is the point negative 1, 0. So negative 1, 0 is located here. Again, you can think about the angle is pi, right? So I can directly say that radius will be 1 and argument will be pi. Okay, directly I am writing. So without wasting time, let's figure out this one. Z equal to r e to the power I theta. This inside number should be converted to polar form. So already we have found r and theta. So r, value of r is 1 e to the power I, theta is pi, power 1 over 4 z. So once we have done this part, then we have to use this formula, theta equal to theta plus 2k pi. So zk equal to 1 times e to the power I pi, that is same. So where we have theta, that should be added with 2k pi, right? Theta plus 2k pi with power 1 over 4. So that means we have zk equal to e to the power I pi plus 2k pi by 4. That means we know that e power m power n, that is equal to e power mn. So that power is coming here. Okay, so again, let me use a table so that you can understand properly. K and zk. This is k. So we will have 4 roots. So 0, 1, 2, 3. Z0, Z1, Z2, Z3. So e to the power I pi plus 2k pi. We are going to input k here by 4. So e to the power I, if we input 0, then it will be pi by 4, right?
Yes, sir.
So pi by 4 is actually 45 degree. I am writing this one. And if we use 1, so it will be e power I.
So 3 pi
It
by
is
4.
3 pi by 4. It is 135 degree. E to the power I 5 pi by 4. E to the power I 7 pi by 4. It is 225 degree. It is 315 degree. Is that okay?
Yes, sir.
Yeah. So we have found total 4 poles. So f of z equal to 1 over z to the power 4 plus 1. That is, this function has exactly 4 roots. or 4 poles of order, what order will be?
Sir, 1.
1. This is M. And the 4 poles are Z0, Z1, Z2, Z3. These are polar form. We don't need to convert to rectangular form. So now step 2. Step 2 is to find the residue. But before that, we have to check which poles are inside the upper circle. So negative R to positive R. And we know that R is tending to infinity. That means this is a big region, right?
Yes, sir.
And whatever part we have found here, this is R e to the power I theta. So what is R here? R is 1. That means we have a circle with radius 1, right? So it is a big circle, big upper circle, but radius 1 circle, a circle with radius 1 will be obviously here. Is that okay?
Yes, sir.
So Z0 is 45 degree is here, Z0,
It's a
1,
first quadrant.
and Z1 will be in second quadrant, Z2 will be in third quadrant, and Z3 will be in fourth quadrant. So now you can think about, out of these 4, which parts are inside the contour?
So Z1 and Z0.
Z0 and Z1. So only Z0 and Z1 are inside. See, Z2, Z3 are outside. So we are doing the same thing, but the problem is a little bit different. It is improper integral. So this is the difference. Okay, so let's find the residue for Z0. For Z0, let's say the residue will be R1. For Z1, residue will be R2. Okay, residue at Z equal to Z0, or Z0 is e to the power I pi by 4. So R1, limit Z tends to A, e to the power I pi by 4. Z negative A, e to the power I pi by 4, f of Z, 1 over Z to the power 4 plus 1. Have you understood? I have written directly.
Yes, sir.
And again, this is a L'Hopital rule. That means L'Hopital rule can be applied, because if we input the same thing here, something minus something, that is 0. And since this solution is coming from this part, so that means if we input the same thing in denominator, we will get 0 in denominator. So 0 by 0. That means we can apply L'Hopital rule. Is that okay?
Yes, sir.
So limit Z tends to e to the power I pi by 4. So derivative of Z is 1. Derivative of Z to the power 4 is 4Z cubed. So finally, the things are done. It is 4 e to the power I pi by 4 cube. So that means this time it is becoming 1 over 4 e to the power I 3 pi by 4, right?
Yes, sir.
Or we can directly write 1 over 4 e to the power negative I 3 pi by 4. This is R1. Is that clear?
Yes, sir.
Now R2. So residue at, once you understand the concept, the problems is easy to solve. So Z equal to Z1. So Z1 is e to the power 3 pi by 4. So R2. Limit Z tends to e to the power I 3 pi by 4. Z negative e to the power I 3 pi by 4 over 1 by Z to the power 4 plus 1. Again, L'Hopital rule can be applied because it is 0 by 0 form. So limit Z tends to e to the power I 3 pi by 4, Z negative e power I 3 pi by 4, by z power 4 plus 1. Can I write directly?
Yes, sir.
It will be 1 by 4. Depending on this part, I can understand that it will be e to the power 3. So that means negative I 9 pi by 4. Is that okay? You will get this one. Because again, we are going to find 1 over 4z cube if we differentiate this part. Is that okay? Just the difference is here. Here we have 1 pi by 4. And here we have 3 pi by 4. So 3 times 3, that is 9 pi by 4. Okay, so step 3. Step 3 is total integral f of z dz, that is equal to 2 pi I sum of all residues. So how many residues we have?
2.
2. So R1 plus R2. So that is 2 pi I. Residue 1 is
So 1 by 4.
1 by 4 e to the power negative I 3 pi by 4 plus residue 2 1 by 4
E to the
e to the power
minus 9.
negative pi 9 pi by 4. So you can also simplify this one as we have done before in previous problem. Is that okay? Okay.
Yes, sir.
So we have solved the complex integral, but actually the result that we have found for complex integral, that will be same for the improper integral. Is that okay?
Yes, sir.
So that means the improper integral that we have found is the right one, right side part. So negative infinity to positive infinity 1 over x to the power 4 plus 1 dx, that is this one. You can simplify this one. So you will get full marks if you come up to this part, okay? Because up to this part you have done a lot of things, so we will not cut any marks, okay? Your marks will not be deducted. So have you understood the total concept of Cauchy's residue theorem and contour integral, okay? And
Yes, sir.
improper integral.
Yes, sir.
One more thing I would like to highlight, that for complex integral like this, we have found the result, but the result is same as the improper integral. So sometimes it is also known as find the Cauchy's principal value. Of this integral, okay? Same thing. That means we have to apply Cauchy's residue theorem. Whatever result that you have on the right side, that is called the Cauchy's principal value. Is that okay? Because it is convergent result. So that means in you can think in simple way, that is whatever result we have found for improper integral, that is called the Cauchy's principal value. Is that okay?
Yes.
Yes,
Have
sir.
you understood the alternative question pattern?
Yes, sir.
It will be in this form: evaluate this integral or find Cauchy's principal value of this one. You will see some problems in your BUX quiz, that is pop quizzes, in week 8 pop quizzes. Okay, so let's start the next topic, that is Taylor and Laurent series. So we have solved so many problems from contour integrals and residue theorem and improper integrals, but let's say we have one integral that is like 1 over 3 plus sine theta d theta, that is from 0 to 2 pi. So we can also solve this type of integrals by using Cauchy's residue theorem. Is that okay? So process is same, but somehow you have to convert the integral so that we can apply Cauchy's residue theorem. So try to learn that one by your own effort. So we are moving to Taylor and Laurent series now. So actually Taylor and Laurent series are the power series. So we have to know what is power series. And Taylor and Laurent were the mathematician. Full name of Taylor, maybe Brooke Taylor, and Laurent is Pierre Laurent. Okay. So Taylor was English mathematician, and Laurent was French mathematician. And also Pierre Laurent was a military officer. Okay. Besides being mathematician, he was a military officer. So we should have respect towards them. So okay, Taylor and Laurent series are actually power series. Power series means, suppose we have e to the power z. You know that e to the power z can be written as 1 plus z squared by factorial 2 plus z cubed by factorial 3 up to infinity. Let's say we have sine z. You are not familiar with e to the power z, but you are familiar with e to the power x. The series that you have learned in Math 110, Taylor series and Maclaurin series, we are thinking about just like that. So if we have e power x, it will be 1 plus x squared by factorial 2 plus x cubed by factorial 3 plus up to infinity. So these things are same for complex integral, complex function, complex valued function. So for sine z, I can remember the formula. That is, for sine z, the series will be z negative z cubed by factorial 3 plus z to the power 5 by factorial 5 negative z to the power 7 by factorial 7 plus up to infinity. We have also a similar series for cosine. Cosine power z equal to 1 negative z squared by factorial 2, and then it will be z to the power 4 by factorial 4 negative z to the power 6 over 6 factorial up to infinity. So these are the preliminary concept. You can see this is a power series, e to the power z, power of z, z power 1, z power 2, z power 3 up to infinity. Similarly, here we have z power 1, z power 3, z power 5, z power 7. So this is a power series. Cosine, for cosine z, we have z squared. And here we have z power 0, that means 1. So z power 0, z power 2, z power 4, z power 6. So that means this is a power series. Is that okay? Can you hear me?
Yes, sir.
So whatever terms we have here, e to the power z, sine z, and cosine z, this exponential function, this trigonometric function, and this trigonometric function, these three functions can be expressed in this way, in power series. So if we suppose trying to find the value for e to the power 2, what result we will get directly from our calculator? If we input 2 here, we will get similar result. Okay, that means in decimal part there will be some changes, but actually we will get the similar result. So the more we take term, the result will be more and more accurate. So this is the advantage of power series. Actually, what algorithm we have in our today's calculator, the behind thing is this power series. Calculator is not doing e to the power 2 directly. Actually, calculator or the algorithm that is defined there, that is based on this power series. So in that power series, actually several terms are there. So that's why we are getting the exact result for e to the power 2, or let's say e to the power pi. Similarly, sine 90 degree. If we use calculator, sine 90 degree will be 1. But if we use the right side, we will get similar result, but result will be more and more accurate if we take more and more term. So okay, so this is the basic thing for power series. Now you can see that whatever powers we have for z, z power 1, z power 2, z power 3, for sine z, z power 1, z power 3, z power 5, all these are positive powers, right? Do you have z power negative 2?
No, sir.
No. So that means all these are of positive powers. But in complex analysis, we may have negative powers. So for positive powers, try to think that whenever we are trying to find e to the power 2, z is replaced by 2, then we can also replace 2 here. That means finally we will get the similar result. Let's say e to the power 2. Let me use my calculator. E to the power 2 is equal to 7.3. So you will get near about 7.3 if you use the right series, right part series. So that means our result is a finite value. That means result is convergent. If we get finite value, that is called convergent. If we have infinity, since it is a power series that is going to infinity, there is no limited terms. So that's why there may be a possibility to have infinity. So our target is to check for which values of z or for what powers of z we have the convergent result. Is that okay? Or we can say in simple way, we have for what values of z or for what powers of z the result is finite. So that's why the concept of convergent is important. This is a theoretical term, convergent. So besides power series, I would like to write some notations here so that you can remember this one if you want to solve some problems. We are familiar with, let's say we have 1 plus z squared. We know it will be a plus b squared formula, that is a squared plus 2ab plus b squared. So if we apply this one, it will be 1 plus 2z plus z squared, right? We can also find 1 plus z power 4 or 5 by using binomial expansion. Clear? But if we have 1 negative z power negative 1, so what will be the result? So actually try to note down this one. It will be 1 plus z squared. This is a formula, plus z power 4 up to infinity. If we have 1 negative z power negative 1, or sorry, let's say 1 plus z power negative 1, it will be 1 negative z positive z squared negative z cube positive z to the power 4 negative up to infinity. One term is positive, then next term is negative, then one term is positive, then next term is negative. So this is for 1 plus z power minus 1, 1 negative z power minus 1. At the same time, if we have 1 negative z power negative 2, it will be 1 plus 2z plus 3z squared plus 4z cube plus 5z to the power 4 plus up to infinity. If we have 1 positive z power negative 2, it will be 1 negative 2z plus 3z squared negative 4z cube plus 5z power 4 negative up to infinity. So whatever series I have written here, all these will be convergent for some domain. So this series will converge if we have modulus of z less than 1. That means all this series will give us a finite value. It may be a complex number finally. If we have this modulus of z less than 1, that means we can think about contour. So it is a circle. That means inside a circle with radius 1 and the interior part, for interior part, this function will be analytic. Is that okay? For now, I am just discussing the theoretical concept, okay? You will understand if we move to the problem solving part. So remember, all these things are valid for modulus of z less than 1. So if we have some other things, let's say we have 1 over 1 by z power negative 1. That is not going with 1 negative z. But the pattern can be same as 1 negative z power minus 1. So we know that for this one, the convergent criteria is modulus of z less than 1. So we have to look for what will be the convergent area for this part, 1 negative 1 over z power negative 1. You will understand from a problem, but try to understand that we may have convergent area if we have an analytic function that is analytic in some domain that is modulus of z less than 1. So let's move to the steps. So all these things, this formula, this 4 terms, 4 series can be thought to be some formulas, okay? Because we are going to apply these formulas in Laurent series or Taylor series. So first of all, let me write the power series. So in power series, let's say we are going to find the power series of f of z. Power series can be defined by, in complex analysis, we can define power series by this way. A sub n z negative z naught power n plus another part is b sub n z negative z naught power n. Here summation, this is called also sigma notation. So it will start from n equal to 0 to infinity, and the later one will be start from n equal to 1 to infinity. So if we simplify this one, you will get summation n equal to 0 to infinity a sub n z negative z naught power n plus summation n equal to infinity, n equal to 1 to infinity b sub n. If we find the reciprocal of this, it will be z negative z0 power negative n. Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay, now we can see that we have total 2 parts. In complex analysis, if we need to find the power series of a function, it may be a rational function, it may be trigonometric function, it may be exponential function, but for your final exam, rational functions are important. Okay, so any function can be written in power series manner, but you can see here we have positive n and here we have negative n. So is that okay? So this is a series, this is an infinite series because it is going to infinity finally. This is an infinite series, this is another infinite series. But the first infinite series is for positive powers and the second infinite series is for negative powers of z negative z naught. So the positive power part, you have positive here. So positive power series is called the analytic part. And the negative power series is called the principal part. Analytic part is also known as Taylor part, or Taylor series, and principal part is known as Laurent part. Or combinedly, we can say the total power series is known now as Laurent series. So if I ask you to find the Laurent series of a function, that means that Laurent series may contain both Taylor part and Laurent part, both analytic part and Laurent, a principal part. So that means combinedly we can say all these two can be now thought to be Laurent series. Is that okay?
Yes, sir.
And also we have to find the coefficients s of n, b of n theoretically, but actually we don't need the theoretical part. The concept of residue, that is Cauchy's residue theorem, is coming from power series. Remember, coming from negative power series. But actually we have learned Cauchy's residue theorem before this part. But actually the sequence that evolves from power series. Then Cauchy's residue theorem came. Is that okay? So
Yes, sir.
let's start Laurent's theorem. The positive power series is called analytic part or Taylor part. The negative power series is called the principal part or Laurent part. A power series may contain both analytic part and principal part, may contain only analytic part, may contain only principal part, or in combined notation we can say the power series is called Laurent series. So we have to know what is Laurent's theorem. A function f of z, that means this one, f of z will be analytic. Suppose f of z is analytic. F of z is analytic inside R1 less than modulus of z negative, z naught less than R2. That means if this is actually representing two circles, if we apply the concept of chapter 1, that is week 1, week 2 videos, so that means you will get to know that this will give you this thing. You will get the inside interior part of this two circle. This is a circle with radius 2 and we have another circle with radius 1. So the shaded region that we have, the function is analytic in that region. Is that okay? In other parts, the function is not analytic. So only for this shaded region, there will be convergent power series. So this function will give us this power series if it is analytic in this region. So this is the theoretical concept. So okay. Now let's move to the steps. Suppose we have a function let's say f of z equal to 3z over z negative 2 4 negative z, and we have a domain or contour, let's say it is contour 2 less than modulus of z less than 4. We have this region. Contour is not the correct word. We have the region 2 less than z less than 4. It is going with this one. That means we can compare with this part 2 less than z negative. Since we have only z, we can think about 0. So z negative 0 less than 4. Is that okay?
Yes, sir.
So actually, if we draw this region, we have z negative z0, z0, z negative 0. It is 1, and we have a circle with radius 2. We have another circle with radius 4. So that means we have to find a series that is convergent based on this shaded region. That means the function that we have here that is analytic inside this region. It is not analytic in this part. It is not analytic in outside part, but it is analytic interior of these two circumference. Is that clear? So the question, complete question will be find the Laurent series. Or we can also say find the power series, or find the analytic part or and principal part, if any. So there will be different question patterns, which is valid for this one. So we have to find a Laurent series for this function. This is a rational function for this region. Okay, so what we have to follow, what steps we have to follow, what algorithm we should follow for finding the Laurent series or power series. Just like Cauchy's residue theorem or contour integral, we have used some steps. So similar type of steps will be followed here. Without the working procedure or steps, we will not get the idea how we can solve any problem. So that's why I always use steps so that you can understand. So step 1. Let's say we have a function f of z equal to something by z negative a, z negative b. So in step 1, you can see we have something by z negative 2 and for negative z. So this is going with that part. So in step 1, we have to use partial fraction. Use partial fraction. You have learned this concept, partial fraction, in your school level or in Math 120. So partial fraction decomposition will be applied here. So we have to use partial fraction so that we can decompose this function f of z to f of z equal to like a by z negative a plus b by z negative b, like that. We have some other process for decomposing, but let me use Easter here so that we can think about the decomposition part later. Okay, so step 1 is to use partial fraction. Step 2. In step 2, we have to find the poles again. Do you remember how we can find poles?
So denominator 0.
Yeah, so find poles. That means the formula is denominator equal to 0. So let's say we have this one, z negative a, z negative b equal to 0. So we will get z equal to a and z equal to b as our poles, right? Or we can say these are the singularities or singular point where the function is not analytic. At 2 and at 4, the function is not analytic. So that's why these are called poles. In step 3, so this is step 1 and step 2. Let me write step 3 here. You have to look that for every poles, we don't need to think about the order of the poles. This time we don't need that. We are going to find Laurent series. So this time we have to check the region. because for every poles there will be a region. You can see we have the region 2 less than modulus of z less than 4. So there must be a region given in your question. Okay, so based on that region we can find the Lorentz series, because if region is not given, then it will not follow Lorentz theorem, because in Lorentz theorem we will get this type of regions. So that's why region will be given in your question. So one thing is that you have to note down, for every pole there must be a given region. Let's say for z equal to a, we have found two poles, z equal to a, z equal to b. So for z equal to a, we have region 1, and for z equal to b, we have region 2. Then what we have to do, because we are going to apply this formulas so that we can express any function in power series, and these formulas are valid for modulus of z less than 1, modulus of something less than 1. Remember, on right side we have less than 1. That is the condition for convergence. So try to understand, every region, that the regions that we have, region 1, region 2, every region should be converted to modulus of something less than 1. Make sure that you have 1 on the right side, then only you can apply these formulas, because in right side we have 1. Is that okay? You have to make sure that on right side you have 1. Is that okay?
Yes, sir.
But sometimes there will be some exceptions, that suppose we have two poles, we have two regions given, but sometimes there will be some exceptions. You have two poles but only one region is given. But what I have written here, for every pole there must be a given region. It may be given in your question, or if it is not, then you have to use your basic skill so that you can find the next region. You will understand. So this is step 3, and in step 4, we have to again get back to the main function, and the main function should be converted to this one now. Let's say this is our function. So get back to f of z equal to a by z negative a plus b by z negative b. So here in denominator we have the factors z negative a and z negative b. But in step 3, let's say we have already the new region, modulus of something less than 1. For region 1 or for pole 1, we have found one region. For pole 2, we have found another new region. Then we have to replace z negative a. That means for a, we have a new region. We have to plug this one here, or we have to use the basic skill so that we can replace this one by these new regions. And finally, we have to apply the formulas. In step 5, apply formulas. You will get your desired Lorentz series. Apply all the formulae that you have. Let's say 1 negative z power minus 1, that is equal to 1 plus z squared plus z cubed plus z to the power 4. I have already this one previously, and we have another, let's say 1 positive z power negative 1 equal to 1 negative z plus z squared negative z cube plus z to the power 4 negative. Still I am in theoretical part. Okay, are you getting bored?
No, sir, not at all.
Okay, so now remember I have given one asterisk sign here because we have to know now what is partial fraction. So there is another concept. But for Laurent series, step 1, step 2, step 3, and step 4, step 5 are enough. Now let's recall what is partial fraction. Partial fraction is always important. In circuit analysis course, you have to use partial fraction. In this same course, that is Math 215, within next 2 weeks, Laplace transform or inverse Laplace transform will be finished. Okay, will be completed. So in that part, you will see the application of partial fraction again. So partial fraction is very important. In Math 120, you have also done partial fraction for solving rational integrals. Okay, so these are the things. Partial fraction is important. So now in partial fraction, we have some types. Let me recall all the types. Type 1, you know all these things. Type 2 and type 3. These are the general types. We have also some other types, but I think you don't need all these things. Just these things are important. So the function f of z that you have, suppose you have something over z negative a, z negative b. So we can write by this way. For z negative a factor, we have a constant a. For z negative b, we have suppose b. Type 2, something by z negative a, z negative b squared, or let's say b cube. So what we have to do, z negative a, this factor will come with a constant a, but z negative b squared will come with z negative b, z negative b squared with c. Is that clear?
Yes, sir.
If still it is not clear, in Math 120, I have a similar video for partial fraction. You will understand partial fraction clearly. I have described all the things there. But for now, try to understand this one. And the third type, z squared negative b. So here we have for z negative a, this is just a factor, simple factor. So z negative a will come up with a. And z squared negative b will be with bz plus c. The things are looking different, but actually you have done the same thing in your school level. Suppose you have x negative a, x negative b. You write this one as 1a by x negative a plus b by x negative b. Is that okay?
Yes, sir.
You can also have a look on your previous studies, so you will get the idea. That is the method of partial fraction decomposition is important. So okay, in step 1, we have to think about what type of function is this one. If it is of type 1, then we can decompose the function in this way. If it is of type 2, we can decompose the function in this way. And if it is of type 3, we can decompose by this way. Remember, if z is squared, that means quadratic term is in the factor, then it will be bz plus c. Okay, at the same time, z negative a, z negative b, besides z negative a, z negative b, it may be also z positive a, z positive b, z positive, 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 positive. So these things are same. Okay. So let's try to solve this problem. I think theoretical part is over. And that means f of z equal to, let me write again the question, that is exponent f of z equal to 3z what I have written here, z negative 2, 4 negative z. Z negative 2, 4 negative z, that is valid for, okay, first of all, let me write this way. Expand f of z in Laurent series. Valid for the region 2 less than modulus of z less than 4. Okay, so step 1, try to recall all the steps. Step 1 is to use partial fraction. So here we have f of z equal to 3z over z negative 2, 4 negative z. So can you please tell me how we can decompose this one? What type will be applied here?
Type 1.
Type 1. So we don't need to focus on the upper part. It may be something. So we have something by z negative 2, 4 negative z. That means we have simple factors here. So a by, that means we can write, we can decompose this one as using partial fraction. Three z by z negative 2, 4 negative z equal to a by z negative 2 plus b by 4 negative z. Now our target is to find a and b so that we can decompose this one. Our focus is on a and b. So for this, next step will be we have to multiplying this part, the term that is in the left side denominator. You have left side and right side. In left side denominator we have z negative 2, 4 negative z. So we have to multiply this term on both sides. Is that okay?
Yes, sir.
Yes, sir.
So if we multiply this one here, z negative 2, 4 negative z, z negative 2, 4 negative z, here z negative 2, 4 negative z. That means this part will be cancelled. Here z negative will be cancelled. Here 4 negative z, 4 negative z will be cancelled. Is that okay?
Yes, sir.
Yes.
So that means we will have the simplified part. From left side we will have just only 3z, and in right side we will have a times 4 negative z plus b times z negative 2. So now we have to find a and b. So this is our equation. Let's say this is equation 1. Since we are starting from the very beginning of Laurent series, so I can't go for shortcut. It's wise to use the actual technique, because same thing will be again you will find in Laplace transform in this same course. So that's why this thing is important. Don't go for shortcut, go for the explanation part. So okay, now our target is to find a. We can input 2 here so that this part becomes 0. Okay, so we can choose any value of z. So let's say we are plugging z equal to 2 in equation 1. So 3 times, these are the positions for z. So 3 times 2 equal to a times 4 negative 2 plus, this part will be 0, right? Or let me write again, b times 2 negative 2. So we have 6 2a plus 0. So let z equal to 4. So that we have b. So 3 times 4 equal to a times 4 negative 4 plus b times 4 negative 2. That is 3 times 4, that is 12. And this is 0 plus 2b. So 12 equal to 2b. So B is equal to 6.
6.
And those who want the shortcut for them, I can show. That is, you can use old form Mathematica, or you can use any online tool. So for this, I can write here. Main function is 3z by z negative 2 for negative z. Sorry, reduce is not working. I think A part will work. Yeah. We have found negative 6 by negative 4. This one is the accurate part. Okay, simplified part will be this one. That means f of z will be z by z negative 2, negative 6 by z negative 4. You can see this function has been expanded in this way. So this is the shortcut technique you can apply your online tool. Clear?
Yes, sir.
But using our basic skill, we have used this one. You can see here A value is 3 and B is 6. But actually we have found this one also here. I can use this Mathematica, or I can use some other online tools. Is that okay? But I will suggest you, please don't go for shortcut, because the same thing will come again in your Laplace transform part. So okay, this function f of z equal to 3z, z negative 2, 4 negative z. So that is now a by z negative 2, b by 4 negative z. So that is a by z negative 2 plus b by 4 negative z. That means now replace a. A is 3, z negative 2 plus b. B is 6, 4 negative z. Now you can see that we have here minus, so we can also use this one. Are you getting the idea? F of z, if we write by this way, we don't need this one. Actually, we are factoring out minus 1 before, so it is this. Whatever algorithm Mathematica is working with, that is actually partial fraction. Is that okay?
Yes, sir.
Yes.
So okay, step 1 is done. Those who are with me from the very beginning of this session, I thank you all, but let me finish this one, then I will conclude the session. Okay, now step 2 is to find the poles. Step 3 is to find the regions for every poles. We can find poles from the main function or from this one also. The main function is 3z by z negative 2, 4 negative z. So actually this pole can be found by denominator equal to 0. So we have z negative 2, 4 negative z equal to 0. So we have actually z equal to 2 and z equal to 4. Is that okay? So step 2 is done. Now step 3. Try to respond, otherwise I'm not getting whether you are understanding or not.
Sir, actually, I'm writing. That's why
Okay, no problem.
একটু দেরি হয়ে response করতে।
I will also deliver the note to you. Okay. So here, now have a look on this comment. For every pole, there must be a given region in your question. If the region is not given, then you have to construct your own region depending on the basic skill. So, okay, have a look on the region that you have. You have 2 less than modulus of z less than 4. And at the same time, have a look on the step. Every region should be converted to modulus of something less than 1. Then we can apply the formulas. So, step 3. We have this pole and this pole. So for pole, z equal to 2. For z equal to 2, our region is given 2 less than modulus of z less than 4. can we break down the terms? That is, I have mentioned that in step 3, for every poles, there must be a given region. So we have total 2 poles. For z equal to 2, there will be a, sorry, for z equal to 2, there will be a region. For z equal to 4, there will be another region. So this region can be actually written in another way. 2 less than modulus of z less than 4. We can write this one as, we can break down as 2 less than z and modulus of z less than 4. 2 less than modulus of z and modulus of z less than 4. If we combine these two, we'll get the previous part back, right?
Yes, sir.
So for this pole, for z equal to 2, we have 2 here. So that means we have 2 less than modulus of z. And for z equal to 4, we have modulus of z less than 4. So this is step 3. And in step 3, don't forget that we have to convert every region should be converted to modulus of something less than 1. Make sure on right side you have 1. So up to this part we are done. That is, for z equal to a, we have a region. For z equal to b, we have a region. Now, so modulus of z less than, now we can write by this way, modulus of z greater than 2. Is that okay? Our target is to come up to this part, modulus of something less than 1. Every region should be converted to modulus of something less than 1. This is the convergent criteria. Okay, we can also write by this way. Since less than is already present, so 2 by modulus of z less than 1. Is that okay? This is the concept of inequality. We can write by this way. Is that clear?
Yes, sir.
And you can see we are approaching to this part. Modulus should be on the total thing. So 2 and modulus of 2, same, right?
Yes, sir.
And in assignment 1, you have learned if you have modulus of z1, modulus of z2, you can write modulus of z1, z2. Is that okay?
Yes, sir.
So that means we can actually write two by z less than 1. So see, we have already approached to modulus of something less than 1. Now, for this region, we have to also convert to modulus of something less than 1. So let's do the same thing here. What we can do, modulus of z by 4 less than 1. And now modulus of 4 or 4 is same thing. So modulus of z by 4 less than 1. So we have also found another new region for this. So whatever new region we have found, that will, for that region, the function will be also analytic. Okay. So because we are coming from an analytic function, so it must be analytic for these regions. Is that okay? These are our new regions. But why we are keeping 1 on the right side, less than 1 on the right side? Because in our formulas, the formulas are valid for less than 1, modulus of z less than 1. That is the thing. Is that okay?
Yes, sir.
Okay, let's move to step 4 quickly. Step 4 is to get back to the main function, and where you have z negative a and z negative b, use the new regions. Then you can apply the formulas. With this problem, I will conclude the session. So our main function that has been come from partial fraction decomposition is this one. F of z equal to, step 4, f of z equal to, let me write from this one, 3 by z negative 2 negative 6 by z negative 4. So 3 by negative 6 by I have mentioned in step 4 that these parts should be replaced by the new regions. We have to write this one so that we can have the same thing here for 2. Since we have 4 here, so we have to focus on this region because it contains 4. So that means, or it is coming from 4 part. So we have to rewrite this one. We have to rearrange based on the new region. That's why I have given Easter on this part. Okay, we have to rewrite the thing. Are you getting the idea?
Yes, sir.
Okay. So you can see that for 2, we have found 2 by z. So our target is to keep 2 by z here. So for keeping 2 by z, what should be taken as factor, or what we can take? We can take z. So 1 negative 2 by z. See, we have 2 by z here. 2 by z is coming. Anyhow, we have to make this arrangement so that we can have the new region here. Is that okay?
Yes, sir.
Yes, sir.
So we are writing in factor form, or we can say z is taken as common. Okay. Here we have z negative 4. So z negative 4. So for 4, what should we write here? We should write one expression that will look like z by 4. Is that okay?
Yes,
So
sir.
for keeping z by 4, what should be
So we
taken
can
as
take
factor?
4.
Yeah, we can take 4,
4.
right? Yeah. So z by 4, negative 1. Clear? Is it okay? So
Yes, sir.
now we can also simplify. It is 2 and 3. So from f of z, we are getting 3 by z, 1 negative 2 by z, negative 3 by 2, z negative 4, negative 1. Okay, now step 5 can be applied. That is, we have to use the formulas. So you can remember the formulas are with 1 negative z power minus 1, 1 positive z power minus 1. So 1 negative z, 1 positive z with power negative 1. So you can see, we can write this one as 3 by z, 1 negative 2 by z, and it is 3 by 2. Is it in 1 negative z by 4 form?
No, sir.
So we can bring
We can
minus before.
multiply with minus.
Yeah, thank you. So it will be 3 by z, 1 negative 2 by z, and plus 3 by 2, 1 negative z by 4. So now we can write f of z as 3 by z. If we use the reciprocal, then it will be 1 negative 2 by z inverse. Is that okay?
Yes, sir.
3 by 2, 1 negative z by 4 inverse. Now it is going with the formulas. If we have 1 negative z power negative 1, then we can write 1 plus z squared plus z cube up to infinity. So we are done. Now we can use the formula. That is, step 5 is to use formulas. So f of z equal to 3 by z. Now think about, this is z. 1 negative z power minus 1. So So what will be the result? 1 plus z squared plus z cube. Is that okay? So we can write
Yes, sir.
1 plus 2 by z plus
2 by
2
z
by
whole.
z squared plus dot, let's say. Or let me write another term, 2 by z cube up to infinity. So first part is done. Plus 3 by 2. 3 by 2. It will be also similar. 1 negative z by 4. Think about 1 negative z. 1 negative z by 4. Think about it is z. So we can write it is as 1 positive z by 4. 1 positive z by 4 squared positive z by 4 cube up to infinity. Clear?
Yes, sir.
So we have found the Laurent series. If you are asked to find the Laurent series, if you are asked to expand the function in Laurent series, you will get full marks up to this, but this is enough. But if you are asked to separate the Taylor and Laurent part, you know that there will be some different question pattern. The question may be in another way, that is find the Laurent series or find the Taylor part and an Laurent part, find separate the analytic part and principal part, or equate which part is principal and which part is analytic. So we can also simplify this part. That is for this. Have you understood our problem is solved?
Yes,
Yes,
sir.
sir.
Just now we are writing so that we are writing in another way. That means we are rearranging so that we can have the Taylor and Laurent part, or negative power series and positive powers. You know that a power series can be expressed a power summation a power n z negative z naught power n positive power plus summation b sub n z negative z naught power negative n. It is n equal to 0 to infinity. It is n equal to 1 to infinity. This part is positive power series, so it is called Taylor or analytic. It is called Laurent or principal. So I am discussing about the same thing. We should express in this way if it is required in your question. So let me write again f of z. Can you understand which part is of negative power series? Out of we have total two summation part. First one and second one. Which power is negative power series?
Sir, both are negative power series.
No. You can see it is z squared, z power 1, z power 2, z power 3. These are positive powers. You will understand now.
Oh, yes, yes.
3 by z. 3 by z can also be written in another way. That is 3 z inverse, right?
Yes, sir.
Then 1 plus 2 z inverse plus, if we simplify this one, it will be 4 z power minus 2. Is that okay? Plus
Yes,
this
sir.
8 z power minus 3 up to infinity. So that's why it is negative power series. And we have plus. We have 3 by 2. So this is constant. No problem. And now we have positive power series. We can simplify as 1 plus z by 4 plus z squared by 16 plus z cube by 4 cube. What is the result? 64, right?
64.
Yeah. So that means we can write 64 plus infinity. So we can also simplify 3 by 2 times 1, 3 by 2 times z power 4, z by 4. So we can also do, but now we can separate that this part is called the negative power series, and this part is the positive power series. So you have to focus on the powers of Z. So now you can write that negative power series is called the Laurent part, and positive power series is called the Taylor part. Or negative power series is called the principal part, and positive power series is called the analytic part. Is that okay? So we have found all these things. All the informations are here.
স্যার মানে কনস্ট্যান্টটা সহই তো পুরোটা হচ্ছে টেইলর পার্টটা আর মানে
Yeah. That means the first part is Laurent part or principal part, and the second part is Taylor part.
ওকে স্যার
So these are the steps how we can find Laurent series. So thank you for joining the session.